So we said, for those coming in, OH minus. I would personally take the negative log of this to get the POH, because the POH with that to get the pH is 14 minus the POH. Okay. Which, what do you guys end up getting? Heard 8 something? Okay. Does that make sense for the pH? Is that acidic or basic for a pH? It's basic. Should it be basic? What did we add to the solution? Sodium fluoride. What happens when fluoride hits water? Makes it basic. What's a basic pH? Above 7. Are we above 7? Yes. Does it make sense? Yes. Okay. So that's just a rough approximation, because we still could have done a calculation wrong and our scale of that pH is off. Okay. But at least that makes sense. It is above 7. Okay? So to solve that, what we had to do is go through and use an ice chart. Okay? At that point, we aren't really at a buffer, because our concentration of HF in that case is really, really small. So as soon as I add a little bit of base, it's going to react with all of the HF ion, and now I'm going to be left with a really high pH and no buffering. Okay? So what we want to go through and do is make it a buffer system. To make it a buffer system, I'm going to have to generate some HF. How can I get HF made? So remember our equation. We had F minus goes to how can I get some HF in that equilibrium? We could add hydrogen. So we add an acid. And the process of adding that acid, the acid reacts with the base, causing an equilibrium shift. That equilibrium shift now increases the concentration of HF. Okay? So one of the next steps to do, if we want to get to that pH or get to a buffer system, is now let's go through and add 0.01 moles of HCl. Okay, added to that same solution. So there's a couple things that are important to note here. What happened to the volume? Nothing, which is a good thing as far as you're concerned, because if the volume changes, what does that mean? All of your concentrations change. You must recalculate all of your concentrations. Right? So in this case, we're not changing the volume. All we're doing is adding some acid. So what we get to decide first is how is that acid going to affect our reaction. Okay? We could go through and say the H plus comes in. So if we look at HCl, what can you tell me about HCl? It's a strong acid, so it's going to immediately dissociate into H plus and Cl minus. I can ignore the Cl minus. Why? Go all the way back to our solubility rules, or even our complex ions, our ion effect rules, and we end up finding out the chloride's not going to change our pH, so we don't have to worry about it. So the H plus, what is that H plus going to react with? This is where it gets a little bit tricky. OH minus is the easiest first guess to go for. Okay? But what we're going to do is actually evaluate the species that are determining our buffer. We're going to look at our conjugate partners. We're going to ignore the hydroxide. That H plus is going to react with our fluoride ion. What's it going to make? HF. What reaction arrow should I put in there? Someone said it, and they were correct, or they were right. Yeah, get it? Right arrow. There we go. Okay. Why do we do a right arrow and not the equilibrium? What do we do with strong acids? They completely dissociate. Do they reach equilibrium? No. So when we evaluate our strong acid additions to our weak acid, or strong anything additions to weak acid and base solutions, we do not assume an equilibrium. Which means now when we go through and solve, we get to try and decide how that H plus affects the concentrations of these. Okay? So what we're going to do is start off by saying, what's our concentration of HF to start the reaction? It's a little bit tricky. We're making some assumptions here. How much HF did we start with? 0. There was none. We started with sodium fluoride. What happens with our initial concentration of fluoride? We start with some of that? Yeah. What was that value? 0.1 molar. What did we start with our H plus? 0.01 moles. Okay. How do we determine what happens to our HF? So this isn't an equilibrium question. So now all of our rules on equilibrium are tossed out. So ignore equilibrium altogether. I add strong acid to a base, it reacts, and we generate product. How do I determine how much product is made? I think I heard it there, something about a limiting reagent. We run a limiting reagent calculation. And we go through and see which of those species, either the H plus or the F minus, is our limiting reagent. Whichever that is, it's now completely wiped out, and that value translates over to HF. Okay? We would then also have to account for anything left over, because that leftover can potentially impact the rest of our reaction. Okay? So what a colleague has actually recommended generating in this case is something known as a Barn M chart. All right, we'll draw that out here in just a second before we get into the ice. It's a new system. Okay, you don't have to use it because it is ultimately the exact same as you would do for a limiting reagent calculation, except here it just kind of organizes the ideas a little bit. Okay, so let's. Okay, and then I'm going to expect you to go through and do all of those problems. So we started with our reaction. We said H plus was added, which reacts with what? Our fluoride ion to make HF. Okay. The chart that I suggested was called the Barn M. So we start with B. B standing for doesn't have to be intuitive. Before we add the acid, okay, or before we add our strong acid or base, what were the concentrations before we started? The fluoride was 0.1. Okay, before we do that, to use this chart, when we go through and do a limiting reagent calculation, what units did you use? So this we haven't talked about directly in this class. Limiting reagent calculations, what units? Limiting reagent unit is moles, not molarity. So when we're going to plug things into this chart, we have to make sure that the values we input are in units of moles. So when we started with the 0.1, that was 0.1 what units? Molarity. We need to know how many moles. So how do we convert our molarity into moles? Times the volume. What's our volume of that solution? Was 1 liter. Okay, so here we happen to be nice. So we got 0.1 moles. Was it 1 liter?
Yes.
Oh, okay, cool. Because this is a before we add our strong acid, what's our concentration of H plus? Hasn't been added yet. What's our concentration of HF? Also 0. It has not reacted yet, at least in this case. So we now have our before. Now what do? Now we'll add our strong whatever it is. Okay? So our F and our HF are going to be 0. How many moles of acid did we add? Okay. I definitely did not give myself enough space for this. Maybe I'll sneak it in. So now we can run our reaction. Okay. In the course of the reaction, this is ultimately how we're figuring out our limiting reagent. What we're going to go through and do is subtract by our smallest number. Why the smallest number? Because that's the limiting reagent. Okay, so in the course of our reaction, we would lose 0.01 moles here. What happens to this one? Also lose 0.01 moles. What happens to HF? It's going to have to gain it. So it's going to go up by 0.01 moles. Okay. Now what we can add on here is what would be known as the neutralization, or pretty much just our addition. We add this all up. What's our concentration of H plus? 0. What's our concentration of F minus? 0. Is it really 99? I guess that is. What's our concentration of HF? Or sorry, our moles, 0.01 moles. Oh, yes. Thank you. Okay. So now we've determined the moles of everything initially. Now what happens once we've got our initial moles? Now we'd need the molarity, because now our reaction can go into equilibrium. Now we can push into the ice chart. But to get into the ice chart, we have to have units of molarity. So the last step before we get to our ice chart would be, I am spelling that right, our molarity. So it would be 0.09 moles divided by our total volume, which in this case is 1 liter, because we said the volume didn't change, so that was kind of nice. And 0.01 divided by our total volume, 1 liter. Now we have initial concentrations for our fluoride and HF. Okay? Everybody have what's up here before I erase it? Okay, we will accept that. So what does that, whoops. What does that then mean? Well, now we can go back to our equilibrium. What was our equilibrium expression? F minus goes to HF plus OH minus. What was our initial concentration of fluoride? Or F minus? (0.09). Why is it 0.09 and not 0.1? It just reacted with the acid. It's no longer that 0.1. Remember, we have to take over what happened after we added the acid. That's where we get the 0.09. What's our initial concentration of HF? What did that say? What did you call me? Okay. Now we can go through which way does our equilibrium shift. What's our Q value? 0, which by definition is what in comparison to K? Less than K. Thank you for saying less than. I was going to write the wrong thing. Which means our product values go up. Our reactants go down. By how much? By how much? X. 1x, okay. Our equilibrium concentration, 0 minus x, 0.01 plus x, x. Now what can we go through and do? KB equals, and I'm going to do exactly what I told you guys. No, I'm not going to do that. I'm going to write it out nice and long. You guys can wait for me. Our OH minus times the concentration of our HF times divided by our reactants, we get X times 0.01 plus X over 0.09 minus X. Now we solve for X. What's X give us? Concentration of hydroxide. The question asked for pH, so we still have to go through all those obnoxious conversions. Okay? Work the rest of the problems on this sheet. Let's see, is this going to take me back? Okay. So to give you an idea on this, the barn M, first off, is just a limiting reagent calculation. Okay. So if you want to use that formatting, you're more than welcome to. Your textbook uses something similar. They do a before addition after. So it's very, very similar. They just format it slightly differently. When we go through and do each of these, what you'll end up finding out is, well, first off, for B, we should go through, for B, do we see an equilibrium? Why is there no equilibrium? What's happening in B? We add acid to pure water, which means no equilibrium. The only reason we deal with equilibrium is if we're weak. If we're not weak, no equilibrium. What happens in C? In C, we're adding acid to our sodium fluoride solution. We need to go through and do that barn chart. One of the problems with this one, what happens to your volume? It changes in the course of the reaction. Make sure when you calculate your molarity at the end, that last molarity step, you are converting it accordingly. The very last one, you would be able to go through and do a barn chart as well. Same idea. The last one, you don't have to do an equilibrium. Why not? There's no weak acid or base present. So when you go through and calculate that, you should see that we've added enough acid to completely overwhelm the buffer system, and we're no longer in a weak acid-base system. Sorry we ran long on that one. We will pick up there tomorrow.